So we'll continue what we missed on Monday when we looked at ethanol. So we stopped at the bioavailability. And if you remember from last time, we took that bioavailability is the amount of drug that makes it to the circulation when you take the drug administered via the oral route versus the intravenous route. Because when you give the drug IV, you're simply hitting directly to the plasma or the blood compartment with no interference or no modulation of your absorption or the amount administered by the subject. But when you take the drug orally, you have multiple factors that can usually minimize the amount absorbed. You're not going to have a bioavailability higher than 1 because there is no way that you take a drug orally and it makes it to the circulation and a concentration higher than when you give it directly to IV route. So usually the bioavailability fraction or the F number usually is going to be 1 or less. So it's the amount of drug that makes it to circulation divided by the dose administered. So I give a gram and 0.9 of this gram makes it to circulation, so it's 90%. Okay?
So all the IV drugs have a bioavailability of 1?
It's okay to assume that, but it's simply because you're calculating the bioavailability based on the IV dose. So it's your standard that you're comparing to. So any drug you give via the IV, this is the amount of absorption or the level of concentration that you're using as your 100%. Then you calculate it based on that. So it's a ratio relative to the concentration you achieve when you get the dose IV. So it's your standard goal. So it's okay to assume this 100% or availability of 1. So you don't calculate bioavailability for all these drugs because there is no factors to change the bioavailability. So what can affect bioavailability? And we talked about that last time. First, absorption. We talked that when you have a drug given via the oral route, not all the drugs absorb, although there are multiple examples of drugs that translate the IV and the oral dose 1-to-1. It's 100%, but they are the exception. Most of doses, when you have a physician calling you asking what dose should I use if I'm gonna change this patient from IV to oral, most of the time you tell them double the dose or triple the dose because you're losing half or 2/3 of the dose when you give it orally. But first part that you lose is the absorption itself from the GI tract. So for example, if you lose 70% of the dose, like when you get the digoxin, you only get 70%. So you already lost 30% for the absorption. Then examples such as atenolol, which is too hydrophilic, or acyclovir, which is too lipophilic. When they are absorbed orally, you also lose a great amount of them. Then you have the V-glycoprotein, which we'll discuss hopefully in the article next week. V-glycoprotein is another bump that bumps the drug out from the circulation back to the GI tract. So if you have an inhibitor of the V-glycoprotein, and the example that we talked about last time was grapefruit juice, and you heard about the grapefruit interaction with other drugs last Wednesday. So in this case, inhibitors or modulators of the V-glycoprotein will affect the dose up or down. So if you have an inhibitor of the V-glycoprotein, you most of the time increase the absorption because you're preventing the bump that kicks the drug back. And if you have activators of the V-glycoprotein, you're simply kicking more drug out of the circulation or out of the brain. So the V-glycoprotein takes the drug from the tissues away. So if you inhibit it, you're actually concentrating the drug more in the tissues. Then we talked about the first pass effect. Most of the drugs that are given orally will have to go through the first pass effect, which could be serious loss of the drug. Some drugs bypass that by giving sublingually or even through directal absorption. You avoid part of the first pass effect. But to account for the loss, you calculate the percentage as we talked about it last time, the extraction ratio, which is dependent on the clearance via the liver, versus multiplied by the flow, or the amount of blood that goes to the liver, which is the Q. Then this gives you the value of the extraction ratio. So this is the amount of drug extracted from circulation when the drug passes through the liver. You subtract this from 1, that gives you the amount that makes it out of the liver circulation, times the F, the bioavailability factor or the absorption factor. The outcome of this whole equation is the bioavailability or the absorption ratio. Okay, we discussed this last time, but we're going to go through this example again. So the drug is completely absorbed, which is the minority of the drugs. The F factor or the absorption will become 1. Usually it's less than 1. Then if you have a drug, for example, we talked about the morphine, that the hepatic circulation is cleared 60 liters per hour for a 70 kilogram subject, which is the ideal weight for that's used for most of the calculation as a 70 kilogram. Then if the liver is getting 90 liters per hour, which means for every 90 liters the liver receives per hour, 60 are cleared from the drug. So you're losing 2/3 of the dose that you have. So you're losing around 0.67, which means how much is making it out of the circulation from the liver? It's 1 minus the extraction ratio, which is 0.33. So for every dose you get from the morphine passing through the liver, you only make it out at 1/3 of the dose that you're giving. That's why if you give a morphine orally, you usually give 3 times the dose that you give IV.
Do any of these take into account any kind of like liver toxicity, or is that something that's not, that we'll talk about later?
Liver toxicity from the drug, you mean?
Or when it's breakdown products?
Okay, so most of the drugs are those based on the effective concentration that you actually need to achieve in the circulation. And if this is going to cause liver toxicity, most of these drugs will not make it to the market. So you have actually to prove that giving the drug orally, you still can achieve the concentration and circulation that you need to produce an action, which is your goal. You're not making drug just to make it to the circulation. You're making the drug to have an effect. Then once it makes it to the circulation and effective concentration, then it's fine. If that concentration to reach it, you cause toxicity for the liver or the renal, then that dosage form never makes it to the market, as it is, unless you modify it to improve the absorption or bypass the liver somehow. So to delay the absorption, you can have slow release, and we spoke about them last time, which simply you micro-encapsulate these powders to have some of these microcapsules dissolved at 5 minutes, other group dissolves at like 1 hour, and so on. So you cover the whole 24 hours, and we have formulation that can cover the whole 24 hours. So you take a capsule once a day, then the effect lasts for the whole day. Okay, we covered this last time, the difference between bioequivalence and pharmaceutical equivalence. So a drug to be pharmaceutically equivalent is different than bioequivalent. You can have the same drug manufactured by 3 or 4 different companies, and in some countries you can have up to 10 generic. I know it's the limited number. In the United States you cannot have more than 2 or 3 generics from some drugs, but for any drug to be approved in the market, you have to prove that you have the same components in the same capsules. Like I'm replicating the drug that's made by company A, so I have to have the same ingredients to be pharmaceutically equivalent. Then you have to show that this capsule or this tablet will deliver the same amount to the circulation. Then you become bioequivalent. And some companies fell in this trap when they started replicating other famous companies' products because they did not have the know-how. Some of the production process was kept secrets most of the time. Like one example is the metronidazole, or was marketed under the name Flagyl as antiprotozoal. The first generic introduced was not bioequivalent, although it has the same pharmaceutical component or the same pharmaceutical equivalency, because they did not know that the original company had micro-sized their powder, which means they used very fine size molecules, which may give the metronidazole greater absorbability or greater access to the circulation and achieve a specific concentration. When they replicated that, they did not know this at the beginning, and most of the drug was not effective. So what are the factors that can affect absorption and distribution? First, organ blood flow. So the greater the flow for a specific organ, you would expect that organ will see higher concentration of the drug because you're delivering more blood that's carrying more amount of the drugs. The molecular size, so the smaller the size of most of these drugs will make it more easier for these drugs to cross through membranes or readily cross membrane barriers, which means that you can achieve higher concentration. Lipid solubility, and this is in general, more lipid soluble means more crossing for membranes because the membranes are mostly made out of lipids. Then you will end up crossing at higher concentration. Surface area, and I see those who were here in the morning went over fixed lobe distribution, where the greater the surface area of that organ, the more chances of drugs to cross because they have greater surface area to cross, especially intestine. Plasma protein binding, and this is a factor, an important component that will affect absorption and pharmacodynamic interaction, because most of the drugs, once they make it to the circulation, they're bounded to the plasma protein. And this is a very important site of interaction between drugs where one drug can displace the other drug from protein binding. And as we said last time, it's the percentage of drug that's free that's responsible for the action. The bound drug is not contributing to the action of the drug. At the same time, it's protected from elimination, because as long as you're bound to the plasma protein, the kidney will not be able to get rid of this drug. Tissue binding, and we're going to go over the volume distribution before the end of this 15 minutes. Some of the drugs, once they make it to circulation, part of the drug, and you have to think about this multi-compartment, so it's not that the drug will go to the circulation and stay there. It starts moving across membranes to different tissues. It can be stored to the bone or the fat. So tissues can serve as reservoirs for drugs. Fat and bone specifically can serve as a drug reservoir depending on the chemical nature of the drug. Obviously, for a drug to stay or be kept in fat or bone, it has to be lipid soluble. The distribution into tissue reservoirs can prolong drug action because of slow release, which means the drug can go and get stuck in the bone or the fat for a long time, then gradually release back to the circulation, which keeps the action. Some drugs will have extremely long half-life because they are stored in bones or fat. Some drugs can go up to 28 days half-life. So it's crazy. If you have a toxicity from such a drug, you will be suffering from the side effects for a long time unless you intervene and get an antidote or something. Redistribution, which means the drug is delivered to the circulation, then from there it's redistributed to the highly perfused tissues, which means if you have high perfusion, and one of the organs that highly perfused is the brain, because it's receiving lots of the drug, so it depends on the quality of the blood-brain barrier to protect the brain from this kind of flux of drugs. And this is the barriers. We talked about some of these barriers last time, the CSF and the central nervous system. So we took the quality of the blood-brain barrier and what is made of tight junction most of the time acts as a barrier. Plus, we mentioned that we have the B-glycoprotein bump that pumps the drug back. And for a while it was known as drug resistance bump because it's actually provided protection to the brain from having higher concentration of blood crossing the blood-brain barrier. So whatever makes it across the blood-brain barrier to the brain, this pump kicks it back to the circulation or the CSF. The placenta serves as an important barrier to protect the fetus most of the time because it's not, the two circulations are separated by the placenta, so the drug has to cross that barrier to make it to the fetus. But there is a problem that the pH of the fetal blood is less than the maternal blood, which means if you have a drug that will be ionized in acidic media, once it's unionized in acidic media, once it goes to the fetal, which is more acidic, it will be unionized, then it cannot make it back to the mom, so it's going to be trapped in the fetus circulation, and this is why it's called ion trapping. So you can have entrapping for basic drugs in babies. That's why when you administer a dose for a pregnant woman, you have to realize that the baby will see more of the basic drugs than the acidic drugs. So if you intend actually to treat the baby, you have to use acidic drugs or use higher doses. But also if you're giving a mom a basic drug, you have to make sure that the baby will actually be seeing higher concentration. So you have to take into consideration of this new concentration be toxic to the baby per kilogram. Okay, so this is the last concept we're going to cover today, which is the volume of distribution. So if I take 1 gram of any drug, like say an antibiotic, ampicillin, where will it go? All the calculations mostly are done based on a 70 kilogram, which is the ideal body weight for calculations. And the body fluids for that body weight, and this could be variable a little bit from different books, that you have 20% of the circulation, or 20% of this weight, which is 14 liters, as extracellular fluid, divided into 3 liters of plasma and 11 liters of interstitial fluid. Then the intracellular fluid is around 40%, which is 28 liters, which makes all the total body water as 60% of your weight. So if you're 70 kilogram, you're almost around 42 of this weight as water, total body water. So it depends on the drug that you're given. Will the drug be distributed everywhere in the total blood water, and the volume distribution will be around 42, or will it be only kept within the plasma, so it's distributed within 3 liters, or it will go through all extracellular fluids, so you're expecting around 20%, which is 14 liters, and so on. It's not that straightforward because, as we're going to talk in a few seconds, it's an apparent volume. It's a hypothetical volume. It's not that the maximum drug you'll have will have 42 liters of distribution. Some drugs have way higher than this, and we're going to explain why. The volume in which the drug is dissolved is known as volume distribution, and not all drugs penetrate all spaces. So some drugs are kept out of the brain. Okay, this is just a percentage for you to memorize. It's around 60%. Total body water, 20% out of which extracellular, and 40% is intracellular. So you can actually replace the body weight to be 100. Then you have different numbers. So 60%, 40-20, and within the 20 you have 80-20. Okay, is this clear? So volume distribution is a virtual parameter. It's not an absolute parameter. Why? Because you're only able to assess it by taking a sample from the plasma, which may not reflect the concentration in the rest of the tissue. But you cannot take a sample from muscles or take a sample from bones to see how much the concentration of the drug in the bone or the muscles. So you're taking a sample from a compartment with the assumption that it reflects the rest of the compartments, which is not true all the time. So it's an apparent volume because it's a virtual parameter to account for drug distribution in the various body compartments other than the plasma where you're actually taking the sample. Since we can only measure the concentration of the drug in the blood or plasma compartment, we must find ways to extrapolate that to the total body. So you're extrapolating your calculation based on the plasma compartment. So for example, if I give a gram of drug, then took a sample an hour later, and the concentration is 0.1 gram per liter. Can you expect how many liters is the volume of distribution for this drug? So the total dose you gave is a gram. When you took a sample, it's 0.1 gram per liter. This is the concentration you have in the plasma. So how many liters volume distribution is that? 20? 10. Yeah, 10. The number is 10. So you simply divide the dose that you gave, which is a gram, divided by 0.1. So 1 divided by 0.1 is 10. So volume of distribution is simply the dose that you gave divided by the concentration in the plasma. Similarly, if I want to calculate the dose, and I know the volume of distribution of the drug, and what's my target concentration that I need to achieve, it's the other way. I can rearrange the equation. So the dose will be volume of distribution times the concentration that I want to achieve. And this is called the loading dose. If I want to load the drug to achieve a specific concentration as my first dose, I usually go for volume distribution times the target concentration that I want to achieve in the circulation. This is with the assumption that I'm giving the drug IV. I'm going to give the drug oral, I have to count for the bioavailability factor. I'm going to see how. So is this clear so far? So, for you to understand the idea of apparent volume and what's the difference, suppose you have a fish tank containing a known volume of water that you know and you want to calculate, then you added 10 grams of dye in the tank. Then you took a sample and it's took that milliliter and it's about 1 milligram of dye per milliliter. Okay, you added 10 grams, which is 10,000 milligrams. Okay, so if you calculate that, say, okay, I have 1 gram per liter as a concentration, which is 1 milligram per milliliter equals 1 gram per liter divided by 1,000, which means I have 10 liters. So that's a good assumption, because if it's 1 gram per liter as a concentration and I added 10 grams, so the volume must be 10 liters. Then you come second day, and you found that the sample you took is only 0.1 milligram per milliliter. What do you think happened to the volume? If you calculate volume now, what will the volume be? We went from 1 milligram per milliliter as a concentration to 0.1 milligram per milliliter. So either the dye went away or broke down, or you added 10 times this volume, because now you went from 1 milligram concentration to 0.1. So if we do the math, this means 1.1 milligram per liter, which means I have 100 liters. So either somebody added water overnight, and then now you have 100 liters as volume of distribution, or as the content of the tank, or something else, that you had fish in that tank that was selectively eating this dye, so the concentration of the dye reduced. It's the same idea. When you give the drug to the body, it reaches the circulation and makes it at a high concentration, which is, for example, 1 milligram per milliliter, then it starts distributing to the rest of the body. It's disappearing from the circulation and hiding in the rest of the body, which is the redistribution phenomenon. Then the volume distribution as apparently started to show higher than the normal expected volume distribution, but you calculate based on the blood sample that you take. So distribution could be either total body water, such as ethanol, extracellular water, most of the time it's a large water-soluble molecule such as mannitol, and this is why we use mannitol to get rid of water in cases of edema, because it will go to all extracellular water and start excreting water. Blood plasma, which is most of the very serious drugs, which means if the drug is only bound to the blood plasma protein, chances of high drug interaction is possible, because now most of the drugs will compete for this small volume. Fat solubility, which is one of the trouble making and deciding how to dose the drug, because fat solubility means the drug will go disappearing everywhere and serve as a reservoir for continuous action. And one of these drugs is diazepam, which is one of the anti-anxiolytic drugs. Bone, most of the drugs like fluoride and tetracycline, which is an antibiotic, concentrates in the bone and serve as a reservoir or slow release. Okay, so this is a continuation of the previous slide. Remember, if the drug has high volume of distribution, then the relative plasma concentration will be high or low. The drug has high volume distribution. When you take a sample, will the concentration be high or low? Low, because it's spreading everywhere, high volume distribution. When you take a sample, it's low. But the drug is highly concentrated in the plasma, so the volume distribution will be high or low? Yes, low. So, if the drug has high volume distribution, goes everywhere, when you look at the plasma, it's very low. If So only staying in the plasma, when you look in the plasma, there's very high concentration and very low volume distribution. They go inversely against each other. High concentration in the plasma means it's concentrated in the plasma, volume distribution is low. Low concentration in the plasma, it goes everywhere, high volume of distribution. We'll stop here so you guys can go for sessions. And this is the equation that we talked. The loading dose equal volume of distribution times the target concentration. So let's start with have the presentation for today. Two of you guys have presentations. Yeah, please.
Let's start with the one that is the fatty acid-induced liver steatosis. And have you got your slides on a memory stick? Just a word to the wise. We've had people giving talks before that thought they were going to pull something up on Google Drive or something. It's really hard to get to from here and doesn't always come through very well. Sometimes the PowerPoints on Google Drive created just don't